So just a quick heads up for the plans for the coming couple of lectures. Today we're going to have a full lecture by Yann. Next week we're going to have another lecture for the first hour, and then the second hour I'm going to be doing the practicum. Then on Thursday there's going to be a practicum, and then the second homework is coming out. All right, that was it. Announcements done. All right, I Eclipse. Have a nice lesson.
Okay, recurrent nets and convolutional nets. So I'm going to talk about more architectures today than what we talked about last time, but we sort of laid the ground last time for the sort of components we're going to use in those kind of big architectures that are very popular or very widely used in various contexts. I'm going to start with something I sort of vaguely alluded to last week, but didn't go into details. This idea of hypernetwork. So this is the idea that you have a neural net whose parameters are themselves the output of another neural net, which may depend on parameters or something else, but also on the same input as the network itself. And some people have called this hypernetworks. Really, this is sort of a general form for something that a very old idea that goes back to the 1980s, where you could have, as I explained last week, you could have a neural net determining the weights of another one in a linear manner, for example. So that creates what's called sigma pi networks or product sum or polynomial units, where you have products of states instead of just weighted sums. So you have sort of weighted sums of cross products of different activations of units. So that would be kind of a very simple form of this kind of network. But we can have more complex forms where this H network here could be an entire very large network with millions of connections, and this G network also could be fairly complicated, although very often they are actually fairly simple. Okay, so this is just sort of a little bleeding of the last lecture onto today's lecture, if you want. One thing also I talked about last week is the idea of shared weight. So if you have a module, a neural net or something, could be an entire network, could be just a single layer, it could be just a single unit or a group of units, and you want to somehow replicate this unit because you are interested, for example, in detecting a motif on an input regardless of where it is. Okay, so I don't know, you want to build a machine that detects if the heartbeat and the brainwaves and whatever it is, electroencephalogram or whatever of a patient is normal, and you want to detect an event, maybe heart arrhythmia or something like this. You would have the sequence of signals coming in, and then what you want to do is train a detector that detects this motif regardless of where it appears on the input. So what you have to do is basically build a little neural net and then slide it over the input. Now, of course, if it's in real time, you just reapply the neural net as you shift. But during training, you may not be able to tell the system exactly where the event occurs. It occurs somewhere in this region, but you don't know exactly where. So the way you train a system like this is that you replicate the neural net over multiple locations, and then you do a max of the outputs. Let's imagine this is a detector, so it's got a single output that can be a high score or low score. You do a max over this region, so the system will basically tell you somewhere in there I detected something. And what you can do is now backpropagate gradient to this entire module. And so if the system is partially trained and it detects a motif, it will be the largest output of all of the replicas here, and you will see it on the output. And when you backpropagate, because this is a switch, max is really a kind of switch, and we talked about that last time, the gradient will propagate through that particular instance and will change the weight of that particular instance to tell it, okay, you actually detected a signal. I'm going to change your weight so that your output is even larger, and it will leave the other one alone. But the other ones are replicas; they are the same as this particular network that you just updated. So you have to essentially have a single weight vector that you share among all of those copies, all those replicas. Now, this is a simple case where only one copy actually gets a gradient, but let's imagine that this operation here is something like a softmax. Then, which of the motif within this thing is the closest to what I'm interested in detecting? So you're going to get a non-zero activation for each of those. You're going to plug them into a softmax, and you're going to get outputs for each of those, and you don't know which one is correct. You can do a max now. So now when you backpropagate, you get gradients for every single one of them. And what you have to do is, because the weight is shared among all those networks, you have to sum the contributions of the gradient from all of those copies. Okay, and that's because the weight here is basically there is a branching Y connection that replicates this weight over all of these copies, right? And what we've seen is that when you have a wire that sort of generates multiple copies of itself, if you want, like a Y connection, when you backpropagate, you have to add the gradients, right? So this is sort of a important point, which I'm going to repeat. So if you have a single variable and this variable is replicated, okay, in the forward pass, in the backward pass, when you have a gradient here, you're going to have a gradient here. To get the gradient here with respect to x, it's going to be simply equal to the sum over I of dc over dyi. Okay, so when you have a Y connection going this way, going the other way, it's an addition. Okay, a branching out in the forward prop corresponds to a sum in the backward prop, and vice versa. By the way, if you had a sum in the forward prop, it would correspond to a copy or replication in the backward prop. So this module is its own transpose, if you want. So that's a way to explain why here, basically this W is being branched out to multiple modules, and when we backpropagate, we have to do the sum. Now, PyTorch does that automatically for you. So whenever you backpropagate through a module, the gradient that is computed with respect to the parameters of that module is not written into the gradient field of that parameter vector, but it's actually accumulated. And the reason it's accumulated is so that you have this sort of implicit sum when parameters are shared across multiple copies of a network or a part of a network. They are accumulated.
All right, maybe we want to repeat this sentence once more, just that everyone can actually remember exactly what you just said. No, this one, the last one about the PyTorch accumulation, because it was like a surprise last time. So.
Right. So in PyTorch, as I think Alfredo may have shown you, when you do a backpropagation through a network, the first thing you have to do is set the gradients to 0, right? You have to reset the gradient to 0 before you do the backprop. And it's because implicitly, when you do a backprop through a module, and this module has parameters, the gradient with respect to the parameters is accumulated into the gradient, right? So if you had a non-zero value before and you do a backprop, the gradient you just computed gets added to whatever was there before. And so before you do a backprop, you have to set that to 0. And the reason for this accumulation, this implicit accumulation, is for situations like the one we're describing here, where you have multiple copies of the same network, you're doing multiple backprop, let's say on multiple samples in a batch, or because you have multiple copies of the network looking at different parts of an image, and implicitly you want the gradients to be added to be sort of combined, if you want, into the gradient with respect to the parameters. So that's really the reason why gradients are being implicitly accumulated in PyTorch.
Also, Carl is a bit confused about you said we have a max as a reduction and not a sum. So can you actually clarify the two, right? So the max is the reduction of the output, while the sum, the reduction of the gradient? Okay,
well, why the sum is a reduction of the gradient is just math, right? I mean, basically it's, again, it's an application of a chain world. So if I have a variable, this variable influences other variables, and this variable somehow goes into some, unknown function that produces our cost, right? So let's call this, C. If I wiggle X by something, it's going to cause W1, W2, and W3 to wiggle by the same amount, right? Now, if I want to know by how much C will wiggle as a result of X being wiggled, C will wiggle by the wiggling of Y1 times dC over dy1 wiggling of Y1 plus dC over dy2 wiggling of Y2 plus dC over dy3 wiggling of Y3, right? But those are equal to delta X because all the Y's are equal to delta X, right? So what I get is that the wiggling of C is equal to delta X times dC over dy1 plus dC over dy2 plus dC over dy3, right? Now, if I put this underneath here, I get, and I write it, as a partial derivative as opposed to a differential calculus, I get this. Okay, so that's just the demonstration that if a signal is copied, when you backpropagate, you have to sum up the contributions. Yeah.
Okay.
Right. So these are recurrent nets. So recurrent nets are an example. I lied to you in a previous lecture when I told you that a deep learning system needs to be a directed acyclic graph. You can't have loops in the graph of connections between the different modules. As a matter of fact, you can have loops, but you have to play a trick, which is to unroll the loop. And this is what we do generally with recurrent net. So recurrent net is a network with a loop, and a simple form of it is this one. So you take an input, you run it, which we call h of t at a particular time t, goes into a function g, which is yet another neural net. It takes as an argument this h of t, and it takes the previous state of the system. So zt is the state of the system, and it takes the previous state of the system as well as a set of parameters w. Okay, so this is why there is this delay block here. The delay block says whatever z of t comes out here, I'm going to store it so that I can reuse it at the next time step as an input to that module g. Okay, so this is like a recursive equation: z of t equals g of h of t, z of t minus 1, and w, where time is discretized essentially. Then you take the state z of t, you run it through a decoder, and that produces the output y or y bar, which is a decoder of applied to z. Now, why is this interesting? Because it allows a neural net to have a memory, essentially, right? So you could imagine that the state will store the past history of what happened to X. And this may be useful for processing sequences. Here T is kind of a time index, but it could also be useful for sequences that are not temporal, but that are spatial. And sort of various other situations of this type. But something that has an internal state, and think of a finite state machine, for example, right? If you've taken computer science courses, you know what a finite state machine is. So you can basically represent a finite state machine by a recurrent neural net with an appropriate definition of G. So how are we going to train such a system, such a recurrent net? The idea for recurrent neural net goes back a long time, by the way, and training them with backprog goes back to the 1980s. So this is a very old concept. So the way we train a system like this is that we unfold it in time. Okay, so X, the input is going to be a sequence, X of 0, X of 1, X of 2, etc. X goes into the encoder, produces H. So that goes into the G function again. It takes into account the previous state, Z0, and then produces Z1, etc. Right? So now what we have is an unfolded recurrent net, and it is now a directed acyclic graph. But what we can tell now is that the parameters of the G function are the same at different time steps. So we have an example of this replication of a module inside of a neural net where we have multiple copies now of this G neural net with the same parameters, right? So we're gonna backpropagate through this structure. We're gonna have to sum up the gradients, the contributions of the gradient of each of the time steps, and accumulate them into the gradient for W. And I didn't write it here, but of course the encoder and the decoder also have parameters, trainable parameters, and they are also shared across time. Okay, so here's how you train a backprop net. You unfold it in time, essentially. You do backpropagation in this new network, which is unfolded in time. And when you backpropagate, because the weights are shared across different time steps, the gradients are going to be accumulated for the different time steps. Now, again, in PyTorch, you don't actually need to do this, to think about this explicitly, because when you're going to write your recurrent net as kind of a loop, PyTorch is going to figure out, this is a loop that I need to unfold in time. And when I'm going to backpropagate, I'm going to accumulate the gradient. So this is going to be taken care of for you. But that's essentially what happens. Now, it turns out it's very difficult to train recurrent nets because very often you want to train a neural net of this type with lots and lots of different time steps, right? It could be a long sequence. Let's say you're doing speech recognition, for example, or something like that. The sequence may have several hundred or several thousand input. And so when you backpropagate, you're going to backpropagate through those hundreds of layers, essentially, right? The G functions are can think of them as layers now. And every time you backpropagate through a layer, depending on the gain of that layer, if you want, your gradient may get smaller or bigger. So let's imagine the G function is a linear function. It takes Z, it multiplies it by some matrix, and then adds H, also multiplied by some matrix, and then that's the output, okay? So let's imagine the matrix by which we multiply Z to produce the next Z is just a rotation, right? It takes a vector and it rotates it. So that would be good because the Z vector will preserve its length as you multiply it by W every time. The only thing it does is that it rotates somehow, right? And it preserves its length. When you backpropagate through a matrix that preserves the length of a vector, the norm of the gradient gets preserved also. If you have a gradient of a particular norm, you multiply it by a matrix that basically is just a rotation. The gradient you get with respect to the input has the same norm as the gradient you gave it with respect to the output. But let's imagine now the weight matrix as small values, so that whenever you give a vector, that vector gets shrunk by, let's say, a factor of 2, okay? Just for the sake of the argument. So as you go through the layers, the states kind of shrink progressively. As you backpropagate, you start maybe with a large gradient, but the gradient also is going to get shrunk because the transpose of the matrix also is going to shrink the vector by this essentially the same amount as in the forward pass. So you get what's called the vanishing gradient problem, which is every time you backpropagate through a layer, your gradients shrink and shrink and shrink exponentially, right? You start with a gradient of norm 1, and then you get norm 1/2, 1/4, 1/8, 1/16, etc. So you don't get much of a gradient after 100 layers, which means your recurrent net is going to act as if it didn't have that many layers because, by the time you get to, past a few layers, your gradients are basically completely killed. Conversely, imagine now that the weight matrix by which you multiply Z has a large norm. So it makes the vector Z longer by, let's say, a factor of 2. So every time you go through one of those time steps, your vector grows larger. And when you backpropagate, it's the same thing. The gradient will get larger and larger, explode. That's called the exploding gradient problem. And so, people realized this in the early 90s and wrote papers about this, Yoshua Bengio, Jürgen Schmidhuber, and various other people. And they say, what can we do to fix this? So, of course, if you have nonlinearities like sigmoids in the system, it will limit the explosion, but not the vanishing gradient. And people pretty much sort of abandoned the idea of, most people abandoned the idea of using recurrent nets in the mid-90s. Most people actually abandoned the idea of using neural nets altogether in the mid-90s, but recurrent neural nets also in particular.
So can you say again what is that leads to the norm to grow or actually diminish?
So let's imagine you have a z vector, let's say z of t, and it passes through a module that just multiplies by a matrix, right? You get z of t plus 1 here, and that's equal to just wzt. If you have an input x of t, let's say you just add it to that, but let's say x of t is 0, so we can ignore it, right? So you have this recursive equation where you take a vector multiplied by a matrix, you get a new vector. Depending on this matrix, right? Let's imagine that this matrix is diagonal. Let's say z is 2-dimensional. This matrix is diagonal and has ones. Okay, so basically you see identity, right? You take zt, and it's zt plus 1 is just equal to zt. Let's imagine it's something like this. So this is a permutation matrix. It takes z0, z1, and it flips them. Okay, so zt plus 1 is just the same as zt, but the coordinates have been flipped. Let's imagine I have something like cosine theta. Okay, so that's a rotation matrix. So it just rotates z, right? So all of those matrices have eigenvalues that are equal to 1, both of them. So they are so-called orthogonal matrices, and they don't change the norm. They don't change the length of a vector. They just rotate or change it somehow, right? But what if I use a matrix that's something like this? Okay, so now if I give it a vector, z0, z1, I'm going to get 2z0 here and 2z1 here, right? So here the vector gets longer. If I put 1/2, the vector gets shorter. And of course, you can imagine all kinds of matrices that will, that have like non-zero off-diagonal terms that will, rotate your vector in some ways and stretch it in some other ways and make it either longer or shorter, right? So the problem is that if it preserves the norm, then z kind of keeps the same norm as you go through the layers, and when you backpropagate, you multiply by the transpose of the matrix to get the gradient. So the length again doesn't change. But if you have matrices like this, where the length of the vector changes, this one will cause an explosion of the length of the state, because the length of the state vector gets multiplied by 2 every time you go through a layer. And the gradient also gets multiplied by 2 every time you backpropagate, because you're using the transpose of the matrix to do the backprop, okay? Which also multiplies by 2. This guy, on the other hand, shrinks the vectors, right? So the state will shrink exponentially, and the gradients will also shrink exponentially when you backpropagate. Does that answer the question?
Yes, I believe so.
Okay. Right. So what do we do to prevent the gradients from exploding or from shrinking? So there's a bunch of tricks, and I'm not going to go through the details of each of them, but sort of give you the basic ideas. Some of those are implemented in PyTorch. You can use them. You can just clip the gradients. So basically, you say when I backpropagate, if the gradients get larger than a certain size, I just clip them to a maximum value, or I normalize the length of the gradient vector at every layer. So this is gradient clipping or gradient normalization. Leaky integration, I'm going to keep this off because I'm going to talk about this later. Momentum, that helps a bit, but not much. Initialization, so it's very important that the weights be initialized in such a way that you don't get, by default from the start, you get exploding or shrinking gradient. And the biggest trick, in fact, are tricks that basically change the architecture in such a way that the gradients don't vanish. And this is a trick that we're going to talk about in just a second. Before I talk about this, here is another type of recurrent net, which is somewhat popular for certain applications, particularly in physics, in computer graphics, in sort of various other applications, dynamical systems, time series prediction. So this is a situation where the type of signal you're trying to model is, let's say, a physical observation of something that occurs in the world, and obeys a differential equation. Okay, so you're observing, I don't know, the position of a ball being thrown, or something like that, right? And the state is basically the state of the system you're observing. X would be the observation, and Y would be some sort of prediction of what's gonna happen. So the internal state of the system, the position and momentum of the ball, for example, would be represented by z of t. And you have differential equations like this, which you'd like your neural net to basically learn by observing a sequence of x and y, so just a sequence of x. Okay, so let's imagine that there is this equation that your system belongs to. Obeys, your data obeys. You're going to model it G by a neural net. Okay, and what you can do is discretize this differential equation. By discretizing, you can write the equation here at the bottom. So z of t is going to be equal to z of t minus delta t. So the previous value of z, with a little delta t, which is kind of a small time interval, plus delta t times the g function. And if you put the z of t minus delta t on the other side and divide by delta t, and you make delta t go to 0, you basically get back this differential equation, right? Which would be sort of a discretized approximation of the time derivative of the z vector. Okay, so there's nothing different about this particular network than as the one I talked about earlier, other than the fact that the update rule here, instead of just computing the new z, basically updates the old z with some function. And so you basically have inside of this box here something that copies the last state on the output, and then just adds the new state computing through the g function. There's been a bunch of papers on this over the last few years, and people call this neural ODE, so neural ordinary differential equation. I may come back to this later in a later lecture. Okay, but here is how we fix the issues with recurrent nets. So the problem with recurrent nets, as I said, is the exploding or vanishing gradient problem, and it's due to the fact that there is a sort of essential contradiction in recurrent net, which is that you'd like recurrent net. The reason why you would want to use recurrent net is to be able to store memories, to basically have the system remember what happened in the past in the form of a state vector, z, which in this case here is called h. It's unfortunate, but I'm using here the standard notation from the papers. So sorry for the difference in notation here. But you'd like the neural net to kind of remember what happened in the past. And those sort of recurrent connections, you can think of them as sort of a elementary memory. So the problem is that if the system actually has memory, right? So what is a memory, really? Okay, so let's say we want a system to actually be a memory. There's a very simple way of building a memory system, which is something that people who know something about electronics know very well. Is that you construct a bistable system, a system that can be either in one state or the other state. Think about a pen, that is on a hinge. It's stable in this situation and stable in that situation, but if you put it in the middle, it's going to fall in one of the two, right? So it's a bistable system. You can you can easily build a bistable system through circuits or operations or electronics by basically having a system with, let's say, take a simple sigmoid function, and then take the input, multiply it by some weight, a scalar weight, and add it to the input. Okay, so I'm putting an x value here. And this system here has, let's say, a hyperbolic tangent sigmoid function, right? So the output is, can go above or below, above +1 or below -1. So let's say x is 0 to start with. And let's say the system initially is in the output is close to -1. It may not be exactly equal to -1, but it's close to -1. This -1 is going to get multiplied by a positive weight. Imagine this weight is positive, okay? So here I'm going to get -w. And here I'm also going to get -w because my input is 0. And -w, if w is large enough, is also going to be close to -1. So that system is stable, okay? If I keep running around, it's just going to stay in the same, it's going to find kind of an equilibrium point. And that equilibrium point will depend on the value of w. If I make w very large, it's going to be close to -1. Now, if I start with +1, this system is going to also get stable, but now this state is going to be +w, and then I'm going to get +w here, and the output is going to be again close to +1, and that system is also stable. So that's a bistable neural net, recurrent neural net that can take two states, either close to +1 or close to -1. Okay, if the weight is less than 1 or less than the gain of that sigmoid, the slope of that sigmoid, whatever it is, every time I go around the loop, it's going to shrink, and eventually the state is going to go to 0. But if the weight is large enough, every time I go around the loop, the weight is going to make the output bigger, and that goes into the sigmoid, and at some point the sigmoid is going to be at its fixed point, essentially, and you're going to get a stable state, close to +1 or close to -1. So that's elementary memory, okay? In fact, there are memories in computers that are basically implemented this way. Now, if I change x now, I can make x, let's say the system is in the +1 state, okay, close to +1, and I make the state like -10, the input -10. This is going to override the influence of the feedback, and the system is going to flip into the -1 state and then stay there. Okay. So that's nice because that means that when the input is kind of not so large, then the system remembers what the last large state was, and as soon as the input gets larger than a certain threshold, the system flips and remembers that last large value of x, whether it was large and positive or large and negative. Okay, so that's great because now we can have neural nets that have memory in them. But there is an issue, and the issue is that when you have such kind of memory modules and you stack them, okay, because of right, so you take the state here and multiply it by the matrix. I'm just unrolling the. Well, I shouldn't have drawn it this way, actually. So I have sigmoid, weight, sigmoid, weight, sigmoid, weight. And if I have an input, of course, the input is sort of added here. Okay, at different time steps. Right, so here's the problem. If the system is in a stable state after a few steps, that means it will have forgotten its initial state, right? I can change the state here a little bit. It's going to make no difference to the output because it's going to go back to its stable state. And so the problem with this is that necessarily this will have a vanishing gradient problem. Because what that means is that when I wiggle the initial state, it makes no difference to the output, which means when I backpropagate gradient from the output to the input, I'm going to get 0 because I can do whatever I want to the input. It makes no difference to the output, to the end state, because that's a stable state. It's an attractive state. So if you have a system, a recurrent net, that when you run it to stabilization, it actually stabilizes into a stable state, which means it has memory. When you backpropagate through that chain, you get 0. you get tiny gradients. So Yoshua Benjo in the mid-90s wrote a paper that says basically it's impossible to train recurrent nets because we have this catch-22, this conundrum, this sort of incompatibility. We want to use recurrent nets because they have memory, but we can't train them because when we backpropagate through something that has memory, the gradient vanishes necessarily. Turns out this argument was only partially true. It's only partially true because you don't actually need to have stable states to have memory. So in fact, you can store information about the past in a system that sort of keeps running around. If the system, for example, is a linear system where the matrix rotates the vector, I already talked about this, then there is no information that is lost by rotating the vector, right? Because any vector is going to get rotated and there is no information lost as to the previous state. You can always rotate by the inverse angle. And so that would be a system that actually remembers where you started from, but it doesn't have any stable states. And so the idea that you need a stable state to have memory is actually not correct. So that's the first thing. The second thing is, and this is where I'm coming, is that what you can do is make the system remember by default. So basically make the system be the identity function by default. So the new state is equal to the old state, and then have a neural net that slightly modifies it. And so this starts to look very much like the idea I was talking about earlier here, the differential equation, where what you have here at the bottom is the update equation where the new state is equal to the old state plus something that's computed by a neural net. So that's the trick we're going to use. So here, so this is the gated recurrent unit, which is sort of an elementary module that you can put in a recurrent net. And this was proposed by Kyung-Young Cho, who's a professor at NYU, as you know. So you take the previous state and you basically just run it through and copy it to the output, but it can get modified in two ways. The first way it can get modified is that you can add to it the result of applying some nonlinear function, hyperbolic tangent or something like this, to an input, which itself might be the output of some neural net. It could also, take the previous state into account. You can run the previous state through, some weight or some nonlinear function or whatever. Combine it with that and produce an output by which you're going to modify the state. So by default, the system just copies whatever is before, but it can modify it if it wants. And there's also a gating. So the gating is this multiplication here. And this is why I talked about multiplicative interactions before and hypernetworks and things like that. So basically here, this is a gating that can choose to, so the output here that gets fed to this is either 0 or 1, essentially. Actually, it's minus. It's either 0 or 1 because it's the output of a sigmoid. Here it's inverted for some reason, but you don't need to worry about that. It's somewhere between 0 and 1, and it could be 0 or close to 0 or close to 1, depending on the output of the sigmoid. And this basically says, if it's 1, then this wire is basically transparent. And if it's 0, then the wire is cut, essentially, right? So the past is forgotten and replaced by whatever comes out of this path. Okay? So this is basically a elementary memory unit, if you want, that either keeps its previous state or can erase its previous state, which is caused by this multiplication here. Okay? If the output is 0, then the previous state would be forgotten and replaced by something new. And if it's 1, it will just be copied and updated. Or it can be just updated, but it's pretty close to the identity. And so because it's close to the identity, you don't have this exploding and vanishing gradient. So it's got imperfect memory, if you want, that can be kind of erased or written into. And you have the formulas here at the bottom. So there's a gating vector. So unfortunately, the notations are backwards from mine, but the Z is a gating vector that is the result of applying sigmoid functions to sort of linear combinations of inputs and previous state and some bias. Okay, you could have a whole neural net here if you wanted. Then you have the resetting gate. So this is the one that can erase the memory. Again, it's a sigmoid function applied to, again, some weight matrix that takes into account the input, some weight matrix that takes into account the previous state and a bias. And again, this could be an entire neural net, not just a weight. And then you have the update formula. So the new state is equal to the old state multiplied term by term. This is the term by term multiplication of the gating vector. Okay, so this will selectively for each component turn on or turn off the previous state. And then let's get linearly combined with the 1 minus the gating factor with the sort of update. So this is the hyperbole tangent applied to the previous state and the input all combined with weight vectors. Okay, that's the basic unit. You have that as a module in PyTorch if you want to use it. And if you need to have a system that looks at the sequence and remember things from far in the past, that may be a good way to go. So this was proposed in 2014, but quite a long time earlier, in 1997, Ochaiter and Schmidhuber proposed something called LSTM, which stands for long short-term memory. So they were interested in solving this vanishing and exploding gradient problem. And they came up with this architecture, which is slightly more complicated than the one I just explained, the gated recurrent units. You can see GRUs as kind of a bit of a simplification of LSTM if you want. And so this one has ways to, again, reset or forget the past. And to kind of write new values into the activation, which is very similar to the previous one, with a few twists. The circles here again are term by term multiplications. Okay, so rather than going through like the entire detail of this, the lesson of this is that you can build special architectures that will have the property you want. You can sort of engineer the architecture if you want, so that you get the sort of behavior or property that you want. So LSTM were proposed in 1997. They were used for a few things, but not really demonstrated for any practical purpose until the late 2000, early 2010s. With a former student of Jürgen Schmidhuber, who was actually working in Jeff Hinton's lab as a postdoc, and who demonstrated that using LSTM in a good way, you could get pretty good performance on something like speech recognition. And so that started a kind of a new wave of interest in recurrent nets and LSTM in particular. That prompted people at Google, Ilya Sutskever at the time in 2014, to build an architecture called multilayer LSTM. So essentially, you take LSTM modules of the type that I just explained, okay, that are elementary memories. You feed it with a sequence. In this case, he was interested in translation, so you feed it a sequence of vectors that represent words, okay, in a sentence. And each of them goes through one of those LSTM unit. But then you take the internal state of those LSTM at every time step, and you feed it to a second layer of LSTM. And so you get what's called a multi-layer LSTM. And you can think of this second stage of LSTM as kind of computing some sort of abstract representation of the sequence that you get from the input. You stack multiple layers of those. I think he had something like 4 layers. And in the end, you get a single state vector here that, if you train the system properly, will represent the entire sequence of input vectors in an appropriate way. Then to train that system, you have lots of parallel text of sequences of words in one language and sequences of words in the other language. You feed that representation, which you hope will represent the meaning of the sentence, independently of language. You feed it to another multi-layer LSTM. And the way this multi-layer LSTM works is that it's got an LSTM module, it takes a null marker and you run it through multiple layers. And at the output, it produces a word, essentially. It actually produces a distribution over words using a softmax, but you're going to pick one. Okay, so you pick one word out of this, maybe the one with the highest score. And you take that word and you feed it to the input of the next time step. Okay, so now this guy knows what word was produced at the previous time step. You run through the few layers of this LSTM for one time step, produce the next word. Then take this word and feed it to the next time step, and you keep going this way. So this is so-called sequential autoregressive generation of text using multi-layer LSTM. And this system, trained by Elias Escaver, was the first system that showed that you could reach the same performance and even get slightly better performance in some cases for language translation than classical translation system based on statistical models, basically. So this is kind of the first neural translation model that kind of worked, but it was really unwieldy because it was like huge, and you needed a lot of GPUs to run this on, and you need to be really smart. So very shortly thereafter, at the end of 2014, Badana, who was an intern at Mila in Montreal, working with Kyung-Yun Cho and Yocha Benjo. So this group of people came up with this idea that, rather than represent the entire sentence in one vector, at the output, when the system is meant to produce a word in the outgoing sentence, what it should do is pay attention to the correct location on the input that correspond to the same word that you're trying to translate, right? So let's say the input sentence is in German and the output is in English. The word order is very different. And so here comes the time to produce a verb. And in German, it could be that the verb is actually at the end. So you have the system should really kind of pay attention to the end of the sentence to be able to translate that word and produce the verb at the right place in English. So this attention mechanism is basically a multiplicative interaction, which I'll talk about again in a few lectures when we talk about transformers and associative memories. So I'm not going to go into the details of this, but let's just say that this system basically is a soft switch with kind of a softmax that decides among all of these guys which one should I look at. So there's kind of a score that looks at each of those guys and that produces in the form of the mixture of expert that I was talking about last lecture, which will produce a score that will decide which of those guys should you pay attention to at this time. That actually completely fixed the issue. So it allowed those translation systems to be much smaller than what Elias Escaver had proposed. And that really kind of started a whole effort in the industry to kind of use translation system based on this idea of attention. And since then, this idea of attention has really ballooned. It's used absolutely everywhere nowadays. But we'll come back to this in a future lecture. Okay, I should say something. Because of this idea of attention that has really taken the world by storm, people are actually not using recurrent nets that much anymore. They prefer to use systematic attention and not actually use recurrent nets. So LSTM is not used nearly as much as it was, let's say, 5 years ago. It's replaced by architectures like transformers and to some extent convolutional nets. Okay, convolutional nets. So this is the main topic actually of today, because you're going to have homework on this pretty soon and practicums as well. So convolutional nets, and we're going to have a couple lectures on this. This half lecture and the next half lecture, I think, are going to be on convolutional nets. So convolutional nets are, again, use this idea of shared weights, and they're good for sequences, let's say audio or speech, or other type of sequential signals like financial time series and things like that. Images, volumetric images, videos, which means, volumetric images are like, MRIs and CT scans and things like this, or images that come from a depth sensor, video, and, other types of natural language, natural signals, essentially natural signals that come to you in the form of an array, okay, multidimensional array, single, 2, 3, 4 dimensions. And this array has to have some property that nearby values in this array are similar or correlated. Okay, so if you take a photo, any photo, a random photo from the internet, and look at the color values of neighboring pixels, there's a good chance that the color values of two neighboring pixels are actually pretty much the same. Okay? Whereas if you take the color values of distant pixels, they have basically no chance of being the same. So that's the idea of local correlations, right? So nearby values are highly correlated. They are kind of dependent, if you want. So that's one thing. And the other thing is that motifs can appear everywhere. So I told you earlier, the first slide I showed was about, training a convolutional net that could detect a motif anywhere on the input. This is basically convolutional nets are based around this idea that you want to be able to detect motifs regardless of where they occur. So that's the diagram I showed earlier. But we're going to generalize this a bit. So let's take a very concrete example. Okay, why do we need to do this? Because we want to build hierarchical representations of the real world. I'll come back to this. Okay, but let's take a very concrete example here. Let's say I want to be able to recognize character images, but I like to be able to do this independently of the location of the character on the image. Okay, so I want to be able to translate the character, maybe change its size a little bit, and still be able to recognize this character as a C. And I might want to recognize these as well, independently of location. So there's an old idea that people in computer vision and signal processing had figured out a long time ago, which is that you build a detector. So detector, you can think of it as a template. Okay. So here, this template is basically a pattern of coefficients, weights, where white indicates a negative weight and black a positive weight. And here, black is a positive pixel and white is negative pixel or 0. And you take this template and you swipe it over the input. Okay. And whenever the dot product of the pixels with the value in the template is positive and large, you turn on the detector, essentially, right? So let me take this little template, let me put it at the left corner. I have an equal number of positive and negative weights. I get 0, essentially. And as soon as I start hitting a black pixel here, this template can react, but it reacts maximally when it's centered around the endpoint of the C here. And it reacts maximally when it's centered around the endpoint of the C here. So maximum output is represented by black. So this thing here, which is called a feature map, represents the activation of the unit corresponding to computing the dot product of those weights with a corresponding little square on the input, a 5x5 square in this case. Okay, so I take this 5x5 square coefficient, I compute the dot product of those 5x5 coefficients with 5x5 pixels, and I put the result in the corresponding location. Then I shift this template by 1 pixel, recompute the dot product, and put the result in the next location. And if I do this for all location, I get this. Okay, so I get high response here, negative response here when it's white, and basically 0 response outside. The corner detector, I get a vaguely positive response here, but it's not very large, and mostly small responses everywhere else. Same for this guy, okay? So now if I run this with some nonlinearity that thresholds, let's say a value with a threshold or maybe a binary detector, I'm going to get activations wherever this guy was large, okay? So at the endpoints of the C that match this template, and I'm going to get 0 everywhere else. And now it's very easy to plug those 3 images to a linear classifier and decide whether it's a C or a D. If it's got, activations here, it's probably a C. If it's got activations here, it's probably a D, because those things will detect the corners of the D, right? So this guy here detects the upper corner here, high activation here. When I threshold, I get high activation here, same here. And if I shift the D, I also get high activations. They're shifted, but my classifier maybe just computes the sum of all of those values and doesn't care where they are. And so in the end, I can classify a C versus a D by just looking at whether I have positive activations here or positive activations there. So this operation that I just described, where you take a small pattern of coefficients and you swipe those coefficients over an image, that's called a discrete convolution. But it's a different type of linear operation where the weighted sums have two special characteristics. The first one is the weights are localized in the 2D space, right? So not every unit in one layer in this layer is connected to every unit in the previous layer. They're only connected to in the previous layer here. They're only connected to a small neighborhood, and all those units share the same weight. They all share those 25 weights. Okay. So there is this idea of weight sharing. So this is a very elementary convolutional net here that I described. Okay. Think of this as the simplest convolutional net you can imagine. A layer of convolutions with three convolutional masks, three set of weights, that each of which detects a feature, right? A particular motif on the input. Then I get at the first layer feature maps that indicate where those motifs have been detected. And then I have a second layer, which is basically just a linear classifier. And it essentially counts how many activations there are in this layer or that layer and tells me, is this a C or a D? So very simple. You could train this with backprop if you put a sigmoid here at this layer, or maybe even a ReLU, and you have biases. This would work. And you could train this with backprop and imagine that the system will learn those templates for feature detection. So here's the trick for convolutional nets. If we apply backpropagation to an architecture like this, where you have units that have local connections and share the weights among locations, it's a convolutional net, and the system will be able to learn local feature detectors to perform a particular task. Now, this system would be invariant to shifts and distortions and change in shape, because it can detect the motifs wherever they occur, and so it doesn't really care where they are, right? But you do care where they are, if you want to distinguish not just C from D, but also other characters, you probably care about the relative locations of those features. Okay, so let's define what a convolution is. So the normal definition of convolution, here this is in a one-dimensional case, is the output number I. So imagine you have a vector of inputs, the xi's, okay? And it produces a vector of outputs. And basically, each output is the weighted sum of a set of inputs multiplied by weights. So this sum runs over the size of the template here, the template of weights. Could be 25 in the case of the image that we saw earlier. It could be any size, really. And you look at the previous inputs from X. It's a very similar form called cross-correlation. And in fact, in PyTorch and in a lot of deep learning systems, what people call convolution is actually cross-correlation. It's just a convention of how you interpret this J index, whether you have a subtraction or an addition here. So this is actually what PyTorch does. So yi here is equal to a weighted sum of x's over a window, and the weights are those wj's. Okay, and when you shift the window and you use the same wj's, the same w's, the same set of w's, and you apply it to another window that's been shifted by one. So in 2D you have two indices, and you just add them. So that's the definition of the convolution operation. So think of this as a layer, okay, where you get a linear layer, essentially. You get an input, a sequence or an image, or even a 3D image. You can have as many indices as you want. Let's say a sequence. And it applies the same motif of weights to every location of your input and produces an output, which is essentially the same size minus border effects as the input. And it's a result of applying the W to the filter W. So the set of weights W is called either a filter for people who are familiar with signal processing, or a convolution kernel if you're a mathematician. Okay, so we'll talk about a kernel essentially. Those pictures, for those of you who've played with Photoshop and other image manipulation programs, there is an operation called convolutions in most of those things. And there is emboss filters and edge detection, all that stuff. And they basically use convolutions, right? So if this looks familiar, it's because you've seen this before in this context. Okay, so we have an input sequence, an output sequence. To produce one output, we compute a weighted sum over a window, and we multiply by the weights, okay? How do we backpropagate through this, right? So if we get gradients with respect to the output, how do we get gradients with respect to the inputs? And the answer is trivial because it's a linear module. And so to backpropagate through a linear module, you imagine that this is a weight matrix and you transpose that weight matrix. And what that means is that you use the same weight, but backwards. Okay, so to get the gradient of the cost with respect to this particular x here, this x is going to influence multiple y's through different weights. Okay, you're going to take the gradients with respect to all those y's and then multiply by all those weights, and you get the gradient with respect to x. And I've written it here in a formula. So the gradient of some cost with respect to xj is equal to the sum over k, which is the index running over the weights, of the gradient of the same cost with respect to the output now that is at location j minus k. Okay, so you look to the left, okay, because all the a particular x here will send its output to y's that are to the left of it, right? Because of this formula. And so you take all the y's that are to the left of that x, and as well as above, and you compute the weighted sum of the gradients backwards, and you get the gradient with respect to the input. And that's this formula. And this is just like multiplying to the transpose matrix of W, if you think of W as a matrix. But Alfredo will explain this to you in more details this week.
Maybe actually, yeah, the linear one, yeah, but perhaps this one is going to be more in the homework.
Yes.
We'll see.
Okay, so there's two backprops because, this is a module with weights. So we also need to backpropagate with respect to the weights. And this is where the formula for shared weights intervenes. So the gradient of some cost with respect to weight Wj is going to be equal to, of course, you have one input here and a weight that, connects with, so input xi plus j and output y, and you have a weight that connects the two. We've seen that for a linear module, you take the gradient with respect to the output, multiply by the input, and that gives you the gradient with respect to the weight, right? So it should be dc over dw over dyi multiplied by xi plus j. The problem is that now this wj is used everywhere. There's the same wj that's being reused everywhere along this dimension. And so because this weight is shared, we have to sum up the gradients with respect to each of the individual instances of this weight to get the overall gradient with respect to that value, which is shared across location. And this is what this formula tells you. So the gradient of some cost with respect to Wj is equal to sum over locations of the sequence of the gradient of this cost with respect to yi multiplied by the x that this weight Wj connects to yi, okay, which is xi plus j. Okay? It's very nice to be able to understand this. PyTorch implements this for you, of course. You have a convolutional layer that you can just plug into your neural net, and PyTorch obviously knows how to do this. So, and so this is kind of now there's different types of convolutions, and when you create a convolutional layer in PyTorch, it actually asks you about several parameters. So here, this is a dense convolution, regular plain vanilla Gordon variety convolution, where one input is influenced by a window here of three, so the kernel size is 3. Okay, you have the same 3 weights that are reused over and over again, and the window is shifted by 1 pixel, by one step every time. Okay, so each of this guy is influenced by this window of 3, and the guy next to it is influenced by that window of 3, and the guy next to it by that window of 3. Okay, that's regular convolution. This convolution with stride. So convolution with stride is one in which each output is influenced by a window that has been shifted by more than 1 step. In this case here, the stride is 2. Okay, so this guy looks at this window of 3, And now we shift that window by 2 steps, and that gives us the next window. And we compute the weighted sum here, and that gives us the next output. So this is convolution with stride or subsampling convolution. And this basically reduces the spatial temporal resolution of the output. It kind of skips over. It looks at all the values, but it skips over some location. And then there is the so-called skip convolution or convolution à trous. It's called à trous. That comes from the French. So it's not pronounced étras. It's pronounced à trous, and it's in theory spelled with an accent on the A. That means in French with holes, and it comes from the French because the people who proposed this in the context of applied math and signal processing actually called it this way. And there, the idea is that the sum of the weights in the kernels are basically equal to 0. So here, the window over which this guy gets influence is a window of 5, but it skips every other inputs, right? So it looks at this guy, it looks at that guy, and it looks at the 5th guy, but it doesn't look at number 2 and number 3. And this is interesting if you want your convolutional net to basically be able to look at a wide window of inputs without actually having too many parameters or too many weights in your system. Okay, so whenever you create a convolutional net, a convolutional layer inside of a network, you have to feed it those parameters. The stride, the size of the kernel, which could be 1, 2, 3, 4-dimensional. Maybe it stops at 3, I'm not sure. The stride, which is how much you skip, and the skip or the à trous, which is how much you kind of expand, you dilate. Yeah, it's called dilated convolution also sometimes. In fact, I think that might be the name in PyTorch, dilated convolution. All right, so how do we put this into a neural net? So this is basically a convolutional nets. Convolutional nets are architectures that are built by alternating layers of convolutions, pointwise nonlinearities, and sometimes pooling. And pooling is an operation that I haven't talked about yet, which I will in just a second. So this is a depiction of an early neural net called LeNet 5, actually. Actually, it's a kind of a subset of it here that's represented. So again, this is a depiction of the convolution operation. We take here a 5x5 convolution kernel, compute the dot product of all those weights by the pixels that are at a particular window on the input, and that gives us the value of a particular activations in the resulting feature map. And we slide that window over all locations. The result gives us a map here where each pixel value indicates the activation, if you want. Okay. So the first layer of a convolutional net is going to be a set of such convolutions with different convolution kernels. Okay, so each of those 4 convolutions use 4 different convolution kernels. Those convolution kernels are going to be trained with backprop. Okay, so here the one I represented is one that actually results from training. It's not something I built by hand, unlike the example with CND that I showed. We're going to train all of this with backprop. Okay. And the advantage is going to be that the system is going to be able to learn by itself what are the good motifs to detect to actually determine the category or solve the task that we're training it for. In this particular example, the outputs actually pass through a hyperbolic tangent nonlinearity. This is the old style neural nets from the 1980s and 90s. So we were using hyperbolic tangent at the time. Now we're kind of more fond of values, but so what you see here are feature maps, which are the result of doing a convolution with a convolution kernel and then passing the result through hyperbolic tangent after having added a bias. So that's the convolution. Then there is a pooling operation, and the pooling operation is essentially an aggregation of the activations within a neighborhood of a feature map with subsampling. So let me explain this in more detail. I'm going to do this for one-dimensional. Okay, so I have a one-dimensional signal. I apply a convolution to it, let's say 3 with kernel 3. Etc. And the pooling operation, a simple pooling operation will consist in doing the following. We consist in taking two consecutive values and combining them in some way to produce an output. And then you skip and compute the next one. So I'm drawing here a particular type of pooling where there is no overlap between the pooling areas, but you could very well imagine having overlap between the pooling areas. So where you're pooling over 4, for example, and you only shift by 2, so the next pooling actually overlap with the previous one. Okay, but generally there is some level of subsampling in the pooling, which means that if here you have n values here in this signal, and the subsampling ratio s is equal to 2, then what you get here is n over 2. Okay, more generally n over s. If you don't have overlap, if you have overlap, it's a little more complicated. There's like border effects. Okay, now what operation are we going to do here for it to be defined as a pooling? So a pooling is basically an aggregation of values whose output is independent of a permutation. So it's basically permutation invariant. So any function f of some number of parameters that doesn't care about the order of its parameters, basically. So I can apply a permutation to the indices. Okay, so P is a permutation here. And I get the same result. That's a pooling, a perfect pooling operation. What kind of pooling operation do we have? A very simple one is just a sum, right? So basically y equals sum or average this is a big K of xi. Xk, I'm sorry. Right, so that's the average pooling. Pretty popular one also is LP pooling. So this would be sum over k of xk to the power alpha, and the whole thing to the power 1 over alpha. In fact, I should probably write it P this is called LP pooling. So LP stands for LP norm. Okay, so we're computing the LP norm of the values seen as a vector. And a particularly popular one is for P equal 2. So compute the square of all the inputs, sum the square, and then compute the square root. That's LP pooling. Max pooling. Okay, so just figure out which value is the largest, and I put that. This is very popular. In fact, probably the most popular of all pooling functions is max pooling. Then there is something a little funny. Okay, so this is kind of log some exp pooling. And this, depending on the value you give to beta, this behaves like max pooling or average pooling. So if beta is really close to 0, this basically is very much like computing the average of the x's. If beta is very, very large, this is very much like computing the max. And if beta is very large and negative, this is like computing the min. Okay. You can come up with other ways to do pooling, but the most popular one are this one, and perhaps this one with p equal 2. There's some theoretical argument for why this is a good idea, but it's not very widely used. It's used in different contexts, but not necessarily for pooling. And very rarely average pooling is used, but only if you precede this average pooling by some nonlinear operation, like a ReLU, a square, or something. Okay? Now, what is the role of pooling? So the role of pooling is to basically eliminate some information about the position where a motif appears on the input, right? So once I go, if I have a motif here that has been detected on the input, if the motif appears in the first 3 values or in the second 3 value, by the time I get to the pooling area, but the pooling unit will turn on regardless of whether the motif is in the first location or the second location. So by doing local pooling, I eliminate a little bit of information about the precise position of where a particular motif occurs. Okay, and that's what makes convolutional nets so interesting, is because they are robust to variations of the locations of features. Okay, so we take this input, run through the convolutions, run through sigmoids, and then here what is being done is actually an average pooling. And then the result is passed through a hyperbolic tangent. So it's a funny kind of pooling, average pooling with a nonlinearity afterwards. And what you get here, and there's a stride of 2, so that the pixels here at that level are twice the size of the pixels on the input, because we shifted by 2, and so I expanded the size of the pixels so that the image is roughly the same size as the input, but it's really half the resolution. And here's the general idea of convolutional net is that you stack this, right? So the second layer, again, performs convolution. So this guy here is a result of applying a convolution kernel to this image, another convolution kernel to that image, another convolution kernel to that image, another convolution kernel to that image, summing up the results and passing the result through a hyperbolic tangent nonlinearity. Each of those guys, each of those feature maps here, the second stage, look at the feature map at the previous stage with different convolution kernels, so they detect different combinations of features. So you can imagine that if the first layer detects very simple motifs like a corner or an endpoint or something like that, or an edge at a particular orientation, what the second layer can do is detect combinations of those, right? Because it can combine the detection from all or a subset of feature maps at the previous layer and detect conjunctions of different motifs on the previous layer, which you can think of as kind of a higher level features, right? So if the previous layer has a detector that detects horizontal edges, and then another detector that detects vertical edges, the second layer might be able to detect corners by combining the two, for example. And then again, you do pooling and subsampling. So again, this is average pooling with a nonlinearity afterwards. And you get a representation of the input now that has almost no spatial information about it. Do convolutions again, and you get to the output, and now you can train this entire neural net to basically classify character inputs, which here it tells you it's a 0. So here's kind of an animation due to Andrei Karpathy of what multiple convolutions do in a sort of animated graphical way, right? So here he's represented the version where you pad the input so that the output as more or less as a size, similar size as the input. In this case here, the stride is 2, so this is a subsampling convolution, and it's padded the output so that you don't get too small of Let me restart the animation. Okay, so you take a window, compute a weighted sum of the values in the window with the weights, and put the result here in the thing. And the input here is not a single feature map, but 3 feature maps. So you have to compute the convolutions of 3 different weight kernels, or for each of those 3 feature maps, and they have different weights. You add the result, and that gives you the output feature map. And then you have a different set of weights for the second feature map, which is in green at the bottom. So if you have some trouble kind of visualizing this, this may be a good way of doing it. Here's another way. So this is a visualization of some old neural net that I trained, back in the early 90s. This animation actually was produced in 1997, if I remember correctly. So here's the input layer here. You get 6 convolution kernels applied to the input, and then followed by a hyperbolic tangent. And you get those 6 feature maps. And I'm sort of translating the 3 here to see the effect of translation on the representation. Then there is pooling. So whenever a particular motif here shifts by 1 pixel, or after the pooling, it shifts by 1/2 pixel, right? Or if this guy shifts by 2 pixels, then this guy shifts by only 1 pixel. So again, those are using average pooling and then passing the result through a sigmoid, to a hyperbolic tangent with a bias. So you get those can be thought of as kind of low resolution versions of the previous layer, if you want, with sort of different intensities because of the sigmoid and the bias. And then we repeat the process. So the feature map here is a result of applying convolutions to some of those 6 feature maps of the previous layers. Those are 5x5 convolutions in 2 dimensions. And then passing the result through, so adding up the result of all those convolutions with all those 5x5 kernels, and then passing the result through a hyperbolic tangent. And then you do this with different sets of 6 5x5 kernels for each of those. Okay, you get 12 of them, I think, or 16, I can't remember. 16, I guess. And then again, pooling and subsampling. And here the system chooses to kind of keep a lot of sort of linear response by kind of keeping within the range of the hyperbolic tangent. So what you get is kind of a small amount of variation here when you have a large amount of variation there because of this average pooling and progressive reduction in spatial resolution. And then again, there are convolutions here. So here the convolution, the size of the convolution kernel is such that the convolution kernel has the same size as the height of a feature map. So when I do the convolution, I can't shift vertically because the kernel is the same size, the same vertical size of the feature map. So I can only slide it horizontally. So as a result, the resulting feature map is only a one-dimensional vector, if you want, for a different horizontal location on the input, but is only one vertical location because I can't shift the kernel because that feature map is already 5 pixels high and my kernel is 5x5. And this is, so there's 120 of those, and this is the representation of the input image before it goes into a couple layers for classification, which are fully connected. Okay, and what you can observe is that the kind of variation you observe here is relatively mild. There are values that go from black to white or white to black or more gray to less gray, but there is no value that goes from black to white to black and things like that, or very rarely. Whereas here, if you take this particular pixel here that I'm pointing at, as the character shifts, it goes from white to black to white. And what that means is that the surface of the various distorted version, the line formed by the distorted version, the shifted version of that 3, is a very curvy line. Okay, because some values go between +1 and -1 and back, and so that means the curve is very, very curvy. Whereas by the time you get to the top layer, the surface, the line that is in this high dimensional space that corresponds to the shifted version of this 3 is kind of it's not exactly a straight line, but it's kind of straighter. And what that means is that now when you're going to apply a linear classifier to it, the linear classifier is going to be able to basically separate all those shifted version of the 3 from shifted version of the 4, because there will be sort of lines that are separated in that space. Whereas in this space, those lines can be kind of intertwined. Okay, so a general convolutional net, you get something like a normalization. I'll come back to this when we talk about Bash norm in a later lecture. Filter banks, which are convolutions, multiple convolutions, pointwise nonlinearity, some sort of pooling. And you take that stage and you repeat it multiple times. And that's a basic convolutional net. Very often the nonlinearity in modern days is a ReLU, which you're familiar with. And the pooling very often is max pooling, occasionally LP pooling, sometimes one of those log sum exponentials. But don't feel like you're limited to any of those things, right? You could imagine much more complex kind of module at every layer. Here's an example of how you create a convolutional net, but again, Alfredo will tell you a lot more about this. You can create a class, which, the way you create a convolutional layer here is this, NN conv2D, that's a 2D convolution. And what you pass is the number of feature maps on the input, which in this case is 1 because it's just a grayscale image. And the number of feature maps on the output and the size of the kernel, which could be 2-dimensional. So you put it into, you can have different sizes for X and Y. Here it's the same. So we just give 1 parameter. And then the last one is the stride, which in this case is 1. Okay, so you have 4 modules, 2D convolution, and then fully connected layers. And the way you compute the forward is that you apply the ReLU to the convolution applied to the input. Then you apply the pooling. The pooling doesn't have any parameters, so you don't need to create an instance here. It's just, you just call the function. Apply the ReLU again to the second layer convolution, pool again, then sort of transform the whatever output here into a vector, and then apply two fully connected layers. Apply softmax because you want to do classification on the output, and then you can have a loss function afterwards. So that's a very simple convolutional net, and it's kind of depicted here a little more graphically. Although the number of feature maps here is not correct because it's too large for what we're talking about here. So here there is no padding, which means we're doing what's called valid convolutions, which means each output, each layer corresponding to the output of a convolution layer is slightly smaller than the corresponding input, so that the kernel doesn't get off the boundary. And so you get, a shrinkage of the layers because of that, and you also get a bigger shrinkage because of the pooling. Now, here's one thing that's interesting about this architecture. If you take one of those outputs here on the layer at the right, and you try to see how many pixels are connected to that feature, this particular feature here. At that layer, at this fifth layer. Each of those guys, when you back project, is basically influenced by an entire window of 32 by 32 pixels. The input is 32 by 64, but each one of those guys on that layer is influenced by an entire window of 32 by 32. Okay, so you can see an entire character, essentially. And that's because of this pooling and subsampling at every layer. This is another way of defining. This is some guy on was proposed a different way of defining convolutional nets here, giving a name to each of using the NN sequential container in PyTorch, and passing as argument. So an n-sequential is basically a deep learning architecture where you just stack layers one on top of the other. So you don't really have to write like a forward, because implicitly each of those layers are going to be called sequentially, which is why it's called an n-sequential. You can give a name to each of them by passing it a dictionary. And so, the forward function is super simple, right? You just have to call, convnet, essentially. Okay, so here's another example of an old convolutional net, and this one is applied to multiple characters. So very early on, we kind of realized that convnets could be applied not just to a single object, a single character, but to multiple characters. And basically, if you make the output itself a convolution, you will get an answer for each location on the input. So remember I told you that each unit here is influenced by a 32 by 32 window on the input. The neighboring unit to that unit is influenced by another 32 by 32 window on the input, shifted by 4 pixels. Why 4 pixels? Because there are two layers with pooling a size 2. So there's an overall subsampling ratio of 4. And what that means is that the next guy at this layer actually looks at 4 pixel, at a window shifted by 4 pixels on the input. I should probably do a drawing on this to kind of explain in more detail how that works. Before I do this, this is a fun video that you can find on YouTube. This is me, by the way. Back many years ago, around 1992. This was my phone number when I was working at Bell Labs. So this was a demo system that we put together in a PC to be able to do kind of semi-real-time character recognition by grabbing images from a camera, and then I hit a key, and the system kind of locates each of the characters and passes them through the neural net, and then displays the result as it computes. And it was able to handle very unusual styles, which really no other system at the time was able to do. So this is me when I was your age. And this is Donnie Henderson, who was the research engineer who put together the system, and Rich Howard, who was our lab director at Bell Labs. This is at Bell Labs in Holmdel, New Jersey, not very far from here. Now, where does all of this come from? This whole idea of convolutional net comes from biology, actually. This is inspired by biology. So when you look at the architecture of the visual cortex, you see that much of the operations performed by the visual cortex for recognizing everyday objects looks very much like what we now call a convolutional net. And in fact, neuroscientists use convolutional nets as a model of how the visual cortex performs object recognition. So your visual system, there's images that are formed on the back of your eye, on your retina. And then that goes through the optical nerve. The optical nerve has roughly about 1 million fibers. So you get an image that is roughly 1 million pixels. In fact, the resolution of your retina is much more than this. It's more like 60 million or 100 million pixels. But that gets compressed by 4 layers of neurons, which are in front of your retina. And they basically compress the signal so it fits onto 1 million fibers. Because if you had 100 million fibers coming out of the back of your eyes, there would be too many wires. Also, vertebrates are really badly evolved because the wires from the optical nerve have to punch through the retina to be able to get out. And so you have a blind spot in your retina, which is where the wires are coming out of your eye. Invertebrates like octopus and squids and stuff like that have a much better design because their wires come at the back, right? Which is kind of a more logical way of building a retina. So they can have much higher resolution optical nerves. Then that goes into something called the lateral geniculate nucleus, which performs something a bit like a convolution and contrast normalization, a little bit of attention, etc. They use convolutional filters that look like center surround. I'll come back to this. Then it goes to the back of your brain, the back of your head, which is where your primary visual cortex is, an area called V1. And V1 is very much like the first layer of a convolutional net. It's much more complex than that, but it performs a bit of the same kind of operation. Then there's two different pathways for vision, one called the ventral pathway, which is the one that's depicted here, another one called the dorsal pathway, which goes kind of to the top of the brain. And the dorsal pathway is the one that processes motion, localization, and things like this, whereas the ventral pathway processes recognition, like, how do you recognize an object, right? There's two tasks, right? There's a task which is recognizing that this is a pen. There's another task which is, if I want to grab the pen, I need to know where it is, and I need to figure out its orientation. If it's moving, I need to be able to predict its trajectory to be able to grab it. That goes in the dorsal pathway. What we're talking about here is the ventral pathway. If you want some idea of how this is arranged, the diagram on the left here shows that. So there's the what pathway, which is the ventral, and the where pathway, which is the dorsal, with sort of different areas that have cute names, like MT, which means motion, which does motion processing. All of those things interact with each other, of course. So the ventral pathway is this hierarchy where you go from V1 to V2, from V2 to V4. V4 represents sort of intermediate visual features like motifs, forms, parts of objects. And then the posterior inferotemporal cortex and the anterior inferotemporal cortex. And this is where object categories are represented. And this whole process, when you start seeing something, the whole process of kind of propagating through this takes about 100 milliseconds, about a tenth of a second. So you're aware of what you're looking about a tenth of a second after your retina has seen it, if you want. It's pretty fast. There's no time for much feedback in things. So there was this hypothesis that this process was essentially a feed-forward computation. It has to be fast, right? This is what you need to be able to detect predators, for example. So you don't have time to think about it. Okay, so then, so the structure of the primary visual cortex area, V1, was studied by two gentlemen by the name of Hubel and Wiesel in the late 50s and early 60s. And what they discovered was that there were neurons in the primary visual cortex area, V1, that are basically neurons that look at only a small part of the visual field and react to a particular motif, like an edge at a particular orientation, right? So you would show an edge at a particular orientation to a cat or whatever animal they were using, and poke an electrode at a particular neuron in that location. And if you move the edge, there's only one particular location where this neuron will turn on. And if you rotate the edge, there's only one particular angle that this neuron will turn on for, will react to. Okay. Now you go to another neuron near it, and it will react to the same edge at a slightly different location. You go to yet another neuron next to it, and it will react to an edge at a different angle at the same location as the original neuron, right? So we'll have a block of neurons basically that all look at the same location, react to different motifs, edges at different orientations. And then another block of neuron that basically detects the same feature, but at a slightly different location on the input. This is very much like a convolutional layer that I talked to you about. And in fact, the idea for convolutional layers comes from them, right? They didn't call it this way, but that was basically more or less what they concluded. And it's very sort of logical to think about why this has to be this way. It's because, local features can appear anywhere in your visual field. And so you need to have detectors that are basically replicated everywhere in your visual field so that you can detect those features anywhere in your visual field. Because, an object can appear here or it can appear here, and you'd like to be able to recognize it regardless of where it appears. So you need the same feature detectors at various locations. You want shift independence. You also want scale independence. So again, the location of features will change depending on how far the object is. Okay, or depending on the orientation and things like this. So one gentleman by the name of Kunihiko Fukushima, whose name is down here, in the late 70s, early 80s, actually built computer models that were inspired by Huber and Wiesel. And he built a system called the cognitron, and then later another one called the neocognitron, which also were the inspiration for convolutional nets. So he was really interested in sort of reproducing the properties of the visual cortex. So his model had neurons that were kind of biologically plausible and things like this. But this was back in the late 70s, early 80s, so he didn't have backprop. He could not train his system using backprop. He used a unsupervised learning algorithm, basically, to train all of the layers, some sort of competitive. You can think of it as clustering, if you want, a little bit like k-means with some competition, local competition. And this system would learn, semi-useful features, and then it would plug basically a linear classifier or perceptron on top of it. And the system was, very slow and awkward, but sort of able to recognize simple shapes. It wouldn't, beat records on character recognition, but it was sort of an interesting model. So I was inspired by this when I built my first convolutional nets in the late 80s, and basically make it, simple and trainable with backprop. Now, Huber and Wiesel also had the idea of complex cells, which are basically pooling units. Okay, so this idea of pooling comes from them as well. And Fukushima also had this idea. So he had simple cells and complex cells. So we would alternate. Simple cell would be convolutions and nonlinearities, and complex cell would be kind of pooling-like operations that would be alternated. So those are what the first convolutional nets that I played with looked like, back in 1988 or so. And I showed that if you had a limited number of training samples, which were those characters that were drawn with a mouse with, by hand, very small training set, the performance would be improved by using those shared weights and convolutional architectures. Then in 1988, I joined Bell Labs in New Jersey and started kind of building larger versions of those trained on real data sets of data, characters coming from zip codes, essentially, that were given to us by the U.S. Postal Service through the University of Buffalo, the State University of New York at Buffalo. A gentleman there by the name of Sagar Srihari, who is still there, was working with the Postal Service and was going to build this data set. For the time, this was a huge data set. It had 7,300 training samples. By now, it's tiny. This network also is tiny by now, but at the time, it was gigantic, and it took 10 days to 2 weeks to train on the computers we had at the time. And this is sort of a later incarnation of it that was trained to be able to recognize multiple characters. Okay, I'm going to actually stop here, keep the rest for next time, and take questions if there are any.
So how do you get the network to be both invariant and equivariant, right? So convolutions are equivariant, but then the pooling are invariant. So how do you get like a network to be both? Maybe, I don't know.
Right. So maybe we should first define what invariant and equivariant means. Okay. So invariant. So saying that f is invariant to transformation T means that f of T of x equals f of x. Okay, so I transform x by transformation T, I pass it through f, I get the same result. Okay, equivariant means that f of T of x is equal to T of f of x. So for this to be, and I should call this T prime, okay? So there is some transformation T prime which applied to the space of f of x produces the same result as applying T to x, okay? Now, for convolutional nets, convolution is equivariant to translation, to spatial translation. Okay, so So if I have an image, let's say a one-dimensional signal, right, xi. So I index by xi. And my transformation is that, t of x index I is x of I plus a constant. Okay, so I shifted the image, right? I shifted the signal. Then I have the property that f of t of x is equal to t of f of x. If this is a dense convolution. Okay, if it's a convolution with stride, then this translation will be, let's say stride 2, this translation will be by half the amount of this translation. Okay, but for a regular convolution, if I shift the input, the output gets shifted, but otherwise unchanged. Okay, so that's equivariance. And pooling is locally invariant. To translation. And this is not a formal statement because it's not entirely locally invariant. But you can imagine that if I have a pooling operation, if I shift the input by, and the pooling is over size 2, for example, right? Or let's say bigger, like size 5 or something. If I shift the input by 1, it will not affect very much what the output of the pooling is. It will affect it a little bit, so it's not completely invariant, which is why I'm saying this is not a formal statement. But it will not affect much the output. And so it has kind of a smoothing effect with respect to translation, which means that if I translate the input will be changed a lot. Like you may have a very large distance between the input and the translated version of itself. But the distance between the result, after applying the convolution and pooling, the distance between the two outputs of the input and the shifted version will be not that large because of the pooling. Okay, so the pooling builds a bit of robustness or smoothness with respect to shifts of the features on the input, right? If I take a more concrete example, so let's say I have an input signal, like a one-dimensional signal, where I have all zeros, but I have this little motif where I have 2 ones that are separated by one blank. And I have a convolution kernel I'm going to apply to this, which basically matches this pattern. Okay, so when I compute the dot product with everything here on the input, I get essentially 0. But whenever it matches here, my output is going to turn on like crazy, right? So if I swipe this convolution kernel over the input, the output is going to be 0 all the time, except for this one where it's going to be large and active. Now, if I pool, with a stride of 2, or subsampling of 2, now I can shift the input by 1 pixel, and what's going to change is that now after the shifted version, this guy is going to turn on, and the same guy here is going to turn on. It's not going to make any difference to the output, right? Because of the pooling. So that's an example of local shift invariance. If I shift by more than 1, then the next pooling unit is gonna turn on. So it's only local for small distortions. Okay, other question?
No one is asking anything. I think we handle everything backstage here today.
Great, thanks. Let's see. Yeah, I know I don't want to start with like multiple characters and applications. So next week we'll talk about applications of convolutional nets, like in practice, special types of convolutional net architectures that are very popular, things like ResNet. which is some of the ideas that I talked about earlier about in the context of recurrent nets of kind of copying the input on the output. We'll talk about how we use those convolutional nets for things like detecting objects in images, semantic segmentation, and various applications, etc. I'm not going to go into a huge amount of details there because if you really want to learn about this, you should probably take a computer vision course, Rob Fergus's computer vision course, in which he goes into gory details about exactly how you do this. But that gives you some idea. There's also uses of convolutional nets for image generation. I won't talk about this very much, but that's a very sort of interesting area. This particular convolutional net. So this is one of the first practical convolutional nets to recognize characters. This one does not have separate pooling layers. It's basically only convolutions with stride or without stride. I think this one had basically 2 layers of convolution with stride 2, with kernels that are 5 by 5, 8 feature maps in the first layer. 12 feature maps in the first layer, and then 16 feature maps, I think, in the second layer, and then 30 hidden units, and then the output, right? And so the convolutional layers had stride 2, and the reason why we didn't have separate convolution and subsampling and pooling layers is that we just couldn't afford it. The computation was much more expensive if we had separate convolution and pooling. It's much cheaper to directly have subsampling convolutions with stride, and so that's what we used at the time because that's what we could afford. So this system, if I remember correctly, had on the order of 40,000 parameters, and maybe 100,000 connections, something like that, and would take about 10 days to 2 weeks to train on the computers of the time. Nowadays, this can be trained in seconds, essentially.
Yeah, we see next week we are going to train in a few seconds a small convolutional net.
Well, probably the ones you're going to train is LearnNet 5, which is a few years after this one. Yeah, actually 1 year after this one. So the one I showed here. Let's see, this one. This one has separate convolution and pooling, and this one was a few years later. It was actually 1 year later. This was NIPS 89, so just 1 year later. And then a few years later, we had this LearnNet 5 architecture that was basically just a slight play on this. This LearnNet 5 architecture actually ended up using quite widely for recognizing amounts on checks and various other applications. And I'll talk about this a bit next week.
I think people don't realize the fact that the longer it takes to train this system and the less iterations one can have, right, to improve parameters, improve like hyper parameters and so on. So right now we can easily get a good network because we just run it a few times. Before you had to wait a week or whatever. I still remember at the beginning when we were training on ImageNet in the 2012 whatever, it took like a week to actually get a data point, an observation.
Right. Okay, so the most complex neural nets that people train at any time during history for the last 30 years, even more, always take about 2 weeks. Okay.
Yeah.
And because that's about the time you're ready to wait for something to run, right? Without it becoming completely impractical. And so regardless of how many GPUs you have, regardless of how much data you have, regardless of anything, at any point in history, the biggest neural nets applied to the biggest application take about 2 weeks to train. Somewhere between a week and 3 weeks. It's also true of speech recognition systems, by the way, or it was true. Now not so much anymore. So that's pretty much a constant. As hardware becomes better, we just make the networks bigger. We train on more data. We train more iterations. Things like that, right? So what I should tell you is, back in 1988, 1989, it was very difficult to actually collect data it was actually complicated to even like plug a camera on the computer. That was actually a major undertaking. Okay, just to collect data. And scanners were not like
with a serial port, right?
Huh?
With a serial port, there was no USB, right? So it's like
there's no USB. No, this was usually a SCSI port or a parallel port or something like this, or
the 232. No, the
usually you had to buy what's called a video grabbing card, which was ridiculously expensive. You had to put in computers. This was very expensive, like multiple thousands of dollars, with a video camera. And there were CCD cameras, but that's about it. Just having enough memory on the card to actually store the image was already a challenge, because it's not like people had like hundreds of megabytes, right? Just an image that is 256 by 256 was is already quite a lot of memory, even in black and white. So it's all black and white. So that's the first thing. So there wasn't a lot of data, right? You had to talk to people who had spent months, setting up a system and spent a huge amount of money collecting data. Then the computers were, it was just about the time that computers started having floating point coprocessors, so they could do floating point multiplications relatively fast. That appeared in like standard workstations. So standard workstations were like Sun workstations. They cost tens of thousands of dollars each. I had one for myself at Bell Labs, and I couldn't believe it, because when I was a postdoc in Toronto, there was one for the entire department. But those things could do about 1 megaflop, 1 million operations per second. So this is, the systems we have today are more than 1 million times faster. Then to the point that the deep learning framework that I wrote called SN actually had a mode so we could do integer arithmetics, because floating point was just too slow. So we had a mode for integer. Now there are things like this too that are coming back. But so then there was no Python, right? There was no MATLAB. There was no Jupyter notebook or whatever, right? You were running Unix on a workstation. You had Emacs, that's the editor, and you could write C programs. And so what Léon Boutou and I decided to do in 1987, when I was finishing my PhD and he was starting his, was to write something like PyTorch at the time. And we wrote something called SN, and this was the ancestor of PyTorch, TensorFlow, all the things that you see today. They're basically descendants of that early system. But because there was no Python, we had to write our own language, Python-like, right? In fact, it wasn't Python-like at all. It was Lisp. It was a Lisp interpreter. So we wrote a Lisp interpreter, and then we plugged a library that we wrote also of sort of tensor operations. Eventually, we wrote a compiler for it, a little bit like TorchScript, if you want. But that's what we used, and nobody else had that. So that gave us superpowers. And they had a big advantage, which were that we were the only people able to train convolutional nets, because we had invested all this time in writing this software. But the bad news was that nobody else could train convolutional nets. And so a lot of people basically didn't want to get into this, because they didn't want to spend the time writing their own neural net framework and convolutional net training environment, because that would require a year or two of writing software and not doing anything else. And so then we gained this reputation that only people like us could train convolutional nets. But it's just because we had invested the time to write the tools and the software. Now we can just download PyTorch, right? But back then, you had to write your own interpreter. So this is why those ideas were so pretty, self-evident, but implementing them at the time was really, really, really hard. And you had to really believe in them to be willing to invest the time to do it. So that's the story.
All right, that's pretty much it. So we see each other again on next week. Again, tomorrow office hour, Friday office hour. Deadline for the homework is going to be actually Thursday. We have one more lecture, 2 more labs before that. Have a nice week, everyone. Bye-bye.
Have a nice week. Yeah. to answer that question, this was coded in C, not C++, which didn't exist in 1997.
All right. Bye-bye.
All right. Take care.